Welcome to the 29th lecture video for Physics 4C. We continue our semi-historical discussion of particle physics in this lecture. Having introduced the neutrino in our last lecture, we turn our attention to the particles that may explain the mysterious force that binds the atomic nucleus together. We first describe some considerations that went into Yukawa's prediction of existence of a meson, or a middleweight particle, which mediates the nuclear force between protons and neutrons. In searching for this meson, today known as pions, experimentalists also discovered the muon, sometimes called mu lepton. This is a beginning of a particle Jew, as there will be so many more new elementary particles discovered that Lamb of Lamb shift in hydrogen fine structure joked in his 1955 Nobel acceptance speech. I have heard it said that the finder of a new elementary particle used to be rewarded by a Nobel Prize, but such a discovery now ought to be punished by a $10,000 fine. The next group of particles we will look at are called strange. Initially, for their strangely long lifetime, we will describe the conserved strangeness and the prediction and discovery of a new baryon with the strangeness of -3, following Gell-Mann's Eightfold Way model. We are at the cusp of introduction of the quark model, which is the start of what we today call the standard model of particle physics. We will introduce the quark model in the next lecture. This is what your textbook starts chapter 11 with, but I think now is the appropriate time for us to address this now. So it comes down to the question of the types of elementary interaction. And I know when I teach physics 4A, I tell you about all these contact forces. Turns out none of those contact forces are elementary interaction. And up until this point in your physics education, we have only dealt with two elementary interactions, gravity and electromagnetic. All the kinds of contact interaction at the very elementary level, they are electromagnetic interaction. Electromagnetic interaction between atoms in my hand and the atoms here. When you put them close, yeah, okay. So when we were looking at the atomic nucleus earlier, that was the first indication that this might not be all the interaction that's out there that can explain our universe. Because when you look at this atomic nucleus, it cannot exist if this is all there is, right? So you might look at, okay, so beta decay, that's a nuclear interaction, and that it involves some kind of interaction that doesn't involve electromagnetic force, because this neutrino is electrically neutral, so it probably couldn't have anything to do with the electromagnetic interaction. But when you look at these types of beta decay type of interaction carefully, it turns out that the properties of beta decay, it doesn't really fit in. So there's some kind of new interaction that's involved here. But it's not the new interaction that would explain this. Here's one reason that I can tell you actually. So this kind of new interaction, it involves the new particle neutrino, right? And what's the one defining characteristic of a neutrino?
Electrically neutral.
Okay, that's one. How did we infer that it's electrically neutral?
Conservation of charge.
Okay, I guess you could do it that way. Okay, so why couldn't there be two neutrinos? That's one positive, one negative. So there was one other experimental fact that we had to fit that made us infer that it's electrically neutral. What was that experimental fact? We don't detect it. It is virtually undetectable. So the fact that it's virtually undetectable also kind of excludes this as participating in whatever interaction this is. Because if there's one thing you can say about this this nuclear interaction is that it's a very strong interaction. Whatever it is, it must overcome electrostatic repulsion between protons. So this is a very strong interaction. And if this neutrino participated in that strong interaction, then we would have detected it, electrically neutral or not, because it would have interacted with the other atomic nuclei around it, and we would have somehow seen it. And not by electromagnetic interaction, but by that other type of strong interaction. So whatever interaction this neutrino participates in, it's not the strong interaction that you see here. So the interaction that neutrino participates in, it's apparently yet another type of interaction that's not involved in holding up the nuclei together. So we call it, we give it another name. It's called, I guess, I don't know when particle physicists became more creative, but this name must have been given before they became more creative, because the name they gave to this interaction was, any guesses? Well, this is what they called it. They called it weak interaction. So the theory of beta decay, which if you want to look up the names, the people who came up with the theory of beta decay were Pauli, as I mentioned. He's the guy who suggested the neutrino. But actually the name neutrino wasn't from Pauli. He wanted to call it neutron before we had a neutron. So the name neutrino comes from a guy named Enrico Fermi. He's an Italian physicist. I think he came to US during World War, or around World War II. So in US, there's a national lab called the Fermi Lab. Guess who that's named after? Enrico Fermi is the one who came up with a theory of beta decay that correctly predicted some of the decay rates. And that is the theory of weak interaction. And the picture that I'm presenting here is not actually the full theory of interaction. You saw in the little diagram, you saw there were two mediator bosons for the weak interaction, W boson and Z boson. They are apparently not drawn here. So the correct version of the Feynman diagram for weak interaction actually looks like this. Neutron turns into proton, emitting a virtual boson, virtual, I guess, W minus boson, and this decays into electron and neutrino. So that's what the full picture is. Let's not get into that right now. So this is a new type of interaction, but it's entirely separate from the interaction that's holding the nucleus together. So, which means there's yet another fourth interaction. It's kind of, so with the particle physics, this is going to be a common theme. You start out with a relatively simple description that you thought was the complete description of your universe. Then you have this odd little thing where you have to start introducing new things, and then it explodes into a whole thing. I guess with the forces, we are lucky that the fourth one that we introduced, we think that's the last one. And no one's suggesting any new interactions. And that fourth interaction, we call it strong interaction or strong force. Once again, I suspect these names were given before particle physicists became more creative with their names. So what I want to use the rest of the time today is the early descriptions of this strong interaction. And this is where we pick up description of something that's referred to as Yukawa's meson. I guess this is probably the only place where I can mention the idea of Yukawa potential or Yukawa type potential. So this is the kind of starting place. You start by thinking about what is the requirement on this new type of interaction that we know nothing about. Right? So imagine you are a nuclear physicist in the 30s, 40s. You know enough about electromagnetic interaction, and you know enough about gravity that in the particle interaction, you can kind of ignore gravity. It's kind of spectator in most interactions. So you know enough about electromagnetic interaction, and you know enough about quantum mechanics to know that the quantum mechanics and the theory of electromagnetism has been fully validated in the study of atomic spectra, right? So in the description of the Bohr model, which matches experiment very well, we didn't have to introduce anything new. So that's your starting place. And now you are trying to introduce a new interaction, which must explain this new phenomena. And a type of correspondence principle continues to hold. It's this idea that this new thing that you are introducing must not mess up the old thing. Right? So based on that, you can start to kind of put some constraints on how this strong force should behave. And I guess in the interest of time, I'll give you the one biggest characteristic of this strong force. The biggest characteristic of this strong force is that this must be a short range force. Why? So let me tell you what I mean by short range. How does gravitational and electromagnetic forces depend as a function of distance? 1 over r squared, the inverse of square law, right? These two forces, their forces go as 1 over r squared, or if you look at the potential, their potential goes as 1 over r. And it turns out this type of dependence characterizes a long-range interaction. You can kind of see it. You know, what are the type of structures that are held together by gravitational force? Planet, anything bigger? Solar system, anything bigger? Galaxies. I'm not sure about the universe, but there are like clusters of galaxies, and there are super clusters of galaxies. So gravitationally bound systems, there's no limit to how large a scale it can be. So it comes down to when you do detailed scattering calculation, the scattering cross-section for this type of potential ends up being infinite. There's, however far away you get, you are always affected to some degree. And so electromagnetic forces are also has an infinite range, but the reason we don't see the effect of electromagnetic force in the large scale is reason that there's positive and negative charge. So anything that has a net charge kind of attracts other charge. So the planets are electrically neutral more or less. That's why you don't see it on astronomical scale. So these are the long-range forces. So when we call this interaction short range, that means we are limiting it to somehow this has a different distance dependence than this. And so I just want to make sure that you have some intuition for why we are assuming strong interaction must be short range. Like why?
When I touch the table, I don't come inside the table.
Okay, so you don't see. So you don't see this strong attractive force in the macroscopic scale. All right, so then let's go down to microscopic scale. What kind of range should this have? What's the upper limit on how far away this force can be effective? So you're saying it would not be effective within a millimeter or micron range. I think you can go a lot smaller.
The size of the atom?
Okay, so size of the atom, yeah. So size of atom is about scale of 10 to minus 10 meters, right, an angstrom. Does this strong interaction play any role, any measurable role at 10 to minus 10 meters? Oh, well, that's size of nucleus. This is size of an atom. Two different things. It doesn't suck the electron, but I guess electron actually turns out it doesn't participate in strong interaction. So, maybe. So biggest evidence you can cite to argue that at this atomic scale, strong interaction is negligible is that it's the atomic spectra. When you look at the spectrum of a hydrogen atom, it's completely explained by just the electromagnetic interaction. So if this was some important player, then you wouldn't that would not be the case. So this is actually still long range because interaction at this range is still only mediated by electromagnetic interaction. So okay, so let's just be more specific. Because we know the typical size of nucleus. Typical size of nucleus is about 10 to minus 14 meters, about 10,000 times smaller than size of an atom, and maybe 10 to minus 15. Do I want to call it 10? Let's stick with the 10 to minus 14. So there's a short range. The range of this nuclear force must be about 10 to minus 14 meters. And so Yukawa is the guy who proposed what kind of form this potential can take in order to limit this interaction into this range. And what he guessed was, well, let's hypothesize this potential over this form. So instead of a potential function simply going as 1 over r, he was adding a multiplicative factor to this, or multiplying another factor to it. And the factor he added was the exponential decay. So he was hypothesizing that the potential that can be associated with this might take this form. E to the minus distance over some characteristic length. And based on this experimental observation of the nucleus size, what he would guess is, well, or I guess at the time it would be more like upper limit on the nuclear size. He could guess, well, this characteristic length, maybe it's about 10 to minus 14 meters. And is it kind of intuitively obvious that if the potential is modified by multiplying by this, that would limit the range of your potential? Yes, kind of enough, right? Yes, yeah. I guess we can just leave that there, and that this is the characteristic length that determines how quickly this exponential is decaying. And here's the actually exciting thing. Once you have guessed this much, then there's a method with which you can guess the parameters of the particle that must be mediating this interaction. So we said in the earlier discussion that comes from quantum mechanics that electromagnetic interaction is mediated by a photon, right? So, in quantum mechanics, everything that's a field has a particle associated with it. Everything that's a particle has a wave associated with it. So you can go back and forth. So if you have a strong interaction and there's some kind of field, some kind of influence of force, then there would be a force mediator associated with that interaction. So Yukawa's guess for what that mediating particle is what came to be known as Yukawa's meson. So this leads to what came to be known as Yukawa's meson. And what I'm telling you is that there is a technique for calculating or estimating the mass of this meson. So, and the technique is, and I think this is kind of difficult to emphasize enough, especially in the first 2 semesters of physics, is dimensional analysis. So when you go back and look at the older physics lectures, you might feel like your physics instructors are overemphasizing units. And that's, I understand that perception, and I would blame that perception on the fact that you haven't seen how powerful a technique dimensional analysis can be. Looking at units, it's not all that powerful when you feel like you know all the physics there is to know. You simply calculate the numbers, you're done. You derive the formula, you're done. You don't need to look at the units. Looking at the units becomes useful when you actually don't know that much physics. Here, this strong interaction, I know nothing about it. There's no formula that tells me what it is. Somebody guessed this, so I have this characteristic length, but beyond that, still know nothing about it. I don't know, is there a charge? But what I can do is, I can guess a mass scale that's associated with this length scale. And I can make that association based on the dimensional analysis technique. So let me, it won't take long, so let me just sketch out the consideration we are going through, and let's just do the dimensional analysis and kind of come up with some formula for this mess. So, all right. So for this dimensional analysis, the starting place is this. I have this length scale. So the quantity I'm trying to figure out is the mass of this meson. Sorry, I introduced a new word without defining it. For now, let me call this Yukawa's particle. So I have this new particle, and I want to know the mass of the particle. So all right, I have this mass. And the very first step in dimensional analysis is first guessing what parameters might go into determining this mass. So let me give you a starting point. One of the parameters I think needs to go into determining this is the characteristic length. Right? I mean, that's gotta be one of the inputs. But if I just end here, then I'm kind of screwed because length is not mass. So I need some additional parameters that's going to help make me sense of things here. Any guesses for additional parameters? Physical constants. What physical constants do you think should matter here?
Electric constant?
Now, electric constant probably one, because whatever this is, it's not electromagnetic interaction. So if we are thinking of like epsilon naught, that's definitely not one of the parameters because it's not an electromagnetic interaction.
The speed of light?
Why speed of light? Because it's not electromagnetic. So there must be some other reason for speed of light to be important.
Like special relativity?
Yeah, is that what you're going to say?
I was just going to say it's the speed of causality. So
Yeah, you know, I might be inaudible here. I don't like the argument based on causality. I know there are physicists who argue based on causality. I don't necessarily believe in causality. So, but in the end, it's about it's about special relativity. And once you are dealing with nuclear physics, energy scales are such that relativity matters. Whenever relativity matters, speed of light, it's not the light that's important. It's that this is the universal speed limit. So whenever relativity becomes important, this plays a role, whether it's electromagnetic or not. All right, so that's one more parameter. I don't think that still helps me. This is length, meters per second. I need some way to bring in kilogram, and neither of these have kilogram in it. Any other parameters? Physical constant that might play a role? What physical constants have you seen in this class?
Elementary charge?
Once again, not electromagnetic. Huh? Yeah, Planck's constant. And in fact, so this is a quantum mechanical phenomenon. Whenever you have something that's quantum mechanical, it must involve Planck's constant. If it doesn't involve Planck's constant, then there must be some classical approximation of it. There is no classical approximation of nuclear interaction, so there has to be Planck's constant. And I'm going to write down the reduced version just for fun. I don't know if that'll actually give me better numbers, but I'm just going to do that. So that's Planck's constant. And actually, this is probably a good chance for me to mention these three fundamental constants that's involved in whatever happens to the universe. The three fundamental constants are these: gravitational constant, speed of light, and Planck's constant. And actually there are things you can do by combining these three fundamental constants. Those are called the Planck scale, and you can have fun with those, but we won't get to that today. For today, so whatever this Yukawa's particle is, it must involve the length scale, must involve relativity, must involve quantum mechanics. And let's see if that's enough to give us a unit of kilogram or unit of mass. So, all right, let's see how they combine. So once you determine all the parameters that must go into determining this quantity, then what you have to do is now, how can I combine these in such a way to yield the correct units? You can think of this as a way of eliminating all the wrong answers. Because, like, why am I calling it that way? Like, how are you eliminating all the wrong answers when you combine them in a way to give you a correct unit? So this is how you have used dimensional analysis so far. You have calculated some algebraic answer on an exam or homework, and you are told to check units. Why are you checking units?
Because if units is
Yeah, there's no way. If one quantity on one side is meters per second and the other quantity is hertz, then there's no way these two can be equal to each other. You must have made an algebra mistake somewhere, right? So this is the argument behind this dimensional analysis. Whichever way of combining these quantities there are, if they are combined in such a way that it doesn't give me kilogram, then that particular combination simply cannot be right. So we ruled that out, that particular combination. So by combining them into a form that will only give me correct unit, I'm pre-ruling out all the other algebraic combination of these that simply cannot be right. Now, if you do this correctly, there will be only one unique combination that will give you correct unit. If there are too many parameters here, then you might have to deal with multiple possibilities. Here, I know what I'm doing, so I picked the exactly correct number of parameters to give me the exact correct one unique combination that will give me one unique expression for math. So let's try that. So first thing I need to do is I need to write down the units of each of these. So the Planck's constant in SI units, it comes in the units of joule times a second. And joule is unit of energy, or if I write this all out, it's a kilogram times joule. It's a energy, so it's a meter squared per second squared. The way I remember it is work done is force times distance. So Newton times meter. Newton is mass times acceleration, or kilogram times meter per second squared. So kilogram times, so Newton times meter, so meter squared per second squared times a second. And let me write it down in a way most people who do dimensional analysis do. I don't want to be really tied to SI unit. Unit is more fundamental than SI unit system, the unit of mass, length, and time. So I'm going to use the letters mass, length, and time. So what this is unit of mass times length squared divided by time, or time raised to power of minus 1. Yep. I think the other two are easier. Speed of light, that's meters per second, or length times time raised to power of minus 1. And finally, the length scale, well, I guess it is length scale, so it must have unit of length. Yeah? So these are the units. And this is the kind of hypothesis or working setup with the dimensional analysis. Your working guess or starting point is that whatever this mass is, I want to be able to express it as an algebraic combination of these three quantities, or h bar raised to power of alpha, speed of light raised to power of beta, and the length scale raised to power of gamma. Or if you choose to look at simply the unit quantities, then what you're saying is, well, unit of the left-hand side, mass, is equal to the unit of this, raised to power of alpha. Or so this, ml squared times to minus 1 raised to power alpha times speed of light, length and inverse time raised to power of beta times length scale, L raised to power of gamma. And the unit on the left-hand side is, I guess, to be explicit, really what it is, mass raised to power of 1. So let me actually write it all out completely. It's m, mass, raised to power of 1, length raised to power of 0, time raised to power of 0. Yep. So I will tell you that there is a systematic way to figure out these powers, alpha, beta, and gamma. You can kind of guess from here. When you expand this out, you'll be able to collect like terms. You know, mass raised to some power, that's combination of alpha, beta, gamma. Length raised to some power, that's combination of alpha, beta, gamma. Time raised to some power, that's also combination of alpha, beta, gamma. and then you say this raised to this power is equal to whatever that mass raised to that power is. And you can come up with a system of equations, 3 equations in terms of 3 unknowns, and you can actually do this systematically. You can actually program a program to do this the way you do it in linear algebra. All of that is a little bit too cumbersome for my taste. It takes way too much work for something that's just easier to guess and check. So I'm going to do that instead. And I will tell you my method for guessing and checking. So this is what I see. H bar is special in that that's the only parameter that has quantity of mass in it. So if I get this power alpha wrong, to get the correct power of n, I'm kind of done. There's nothing I can do to fix it. So I must get this alpha correct to get this correct power. So that means there's nothing else alpha can be. Alpha must be 1. Right? Okay. So once I nail that down, then I use the other 2 constants to fix the rest of units. I must somehow cancel out this length and time in the remaining thing. And how you do this guess and check will depend on the setup you have. That's why I was first telling you that there's a systematic way. If you don't feel comfortable guessing and checking, you can just do the systematic way. But the way I'm guessing and checking is I look at one parameter, which is in terms of 1 unit only, which means I don't really have to worry about the length unit. Whatever I come up with the length, just to be for this parameter, I can use this to fix my remainder of length unit. So really all I want to worry about right now with C is the unit of time. I just want to make sure I cancel out unit of time. So as I look at that, what I see is, so this beta must be -1. So that the t to -1 gets canceled out here. All right, so this is -1. Now that doesn't give me correct length unit because I have L to the 2 and then -1 from here. So I still have 1 power of L left. So I would use this lambda to fix that. So this must be -1. So this kind of guessing and checking is a lot quicker than systematic method in most cases. So that's what I'm doing. So with this as a guide, what we would now guess is that this mass, whatever mass of Yukawa's particle is, this is the only combination that gives you the correct unit. The mass must be a combination of h bar raised to power 1 divided by speed of light times this length scale. And this somehow must give you correct unit. So let's correct unit. So let's plug in the numbers and see what kind of number we get. H bar divided by speed of light times, length scale I have to enter, 10 to -14 meters. Let's see. Wolfram alpha is usually smart enough to offer me all the correct units. All right, it offers me kilogram. Kilogram gives me no sense of scale whatsoever. So I'm gonna ignore that and move on to MeV units. So 39 times electron mass. Okay, it's not giving me the number I want. Okay, I get 20 MeV, but I think this is actually enough to show you one thing. So it's heavier than electron, right? Definitely heavier than electron, but it's like 40 times the mass of the electron, but it's lighter than proton. Proton is 2,000 times the mass of electron, so it's somewhere in between, and that's where the name Meson comes from. It's called Yukawa's Meson because it's the mid-weight particle. Its weight is in the middle between the baryons and the leptons. So now the 20 MeV, that's not really the correct number. So the number that Yukawa used must have been 10 to -15 for the nuclear scale. So let me just go back and fix that. And we'll just have the correct number for the next part of the discussion. So this is a kind of a prediction. I'm obviously simplifying some things, but so like in Yukawa's actual paper, there'll be more justification beyond. But the core of the argument is still the same, that if you have the particular length scale, which would give you a short range interaction, then the particle that can be associated with this length scale is very likely to have this level of mass scale. Yeah, and you can kind of see one thing actually. So if you have a long range interaction, like if this was infinity, then what would the mass of this particle, mediator particle, be? Like imagine your length scale that I enter up here is very, very large, like 1 meters. Very, very small mass, right? Does that match what we know about the photon? Massless. Yeah. So the fact that photon is massless is closely associated with the fact that electromagnetic force is a long-range force, or it exactly behaves Coulomb's law, one of the inverse square law. So anyway, so this was Yukawa's prediction that if you have a particle that's mediating this short-range force, then the mass of the particle, just a rough guess, is going to be 200 MeV per c squared. So that's one of the characteristics of Yukawa's meson, and it's a bona fide prediction because he's hypothesizing existence of a particle with a mass that doesn't match any of the known particles. So you know, people are looking for this meson. So let me just quickly tell you the context where people were looking for this meson. The context where people were looking for that meson is in the cosmic rays. Do you guys remember a brief discussion of cosmic ray when we were doing special relativity? No? Yes, no? What are cosmic rays made of? Like what did I think I gave you a short description of what cosmic rays were. Does anyone remember?
Some high energy particle.
Yeah, high energy particle from the universe. So what cosmic rays are? High energy, mostly protons, coming from extra Earth, probably extra solar, possibly extra galactic sources. So let me just show you what's called a picture or artist rendering of what's called a cosmic ray shower. So air shower. Let me. So it's just a rendering to illustrate what's involved in cosmic rays. I guess I don't know how well you can kind of see it. So what I've been calling high energy proton, that's the primary cosmic ray. So this is the initial proton that's impacting our upper atmosphere. And it really doesn't matter what it is. It doesn't matter that it's a baryon, so that it undergoes a strong interaction. So in this interaction point, what it does is because it's so energetic, it produces many different particles. And some of those particles are other nuclei that gets produces, and some of the particles are what's called pion that we'll talk about really quickly, and some of the, I guess that's it. So these pions are what's called the secondary rays. And these secondary rays are composed of, so pions are unstable particles. These unstable particles will quickly decay into additional particles. Pion, pi plus, it should decay into neutrino and muon. So this muon is, I think we've mentioned the muon, right? So this muon is the tertiary cosmic ray particle. You started at the primary high energy proton that produced some very short-lived pion, and then that short-lived pion decaying produced the muon, which is also not that long-lived. It lives for like 2 microseconds. But when people detect cosmic rays on the ground level here, what they are looking for and what they are detecting are these muons. Okay? So before the invention of particle accelerators, this was the only source of unstable particles that don't just exist lying around. They all have really short lifetime scales. This, let's see, I don't know if I remember all the numbers. So muon lives for about 2 times 10 to minus 6 seconds. Oh, this is what the booklet is for. I can look up. So I do know for a fact that the charged pions live for a shorter length of time. So let me just look it up. So pi, lepton summary, Meson quarks. Okay, I'm almost there. Pion is at the beginning of the Meson table. So pi plus mean life is 10 to minus 8 seconds. And that's actually super long. So this lives for about 10 to minus 8 seconds. And I say that's super long because these neutral pions, they actually decay more quickly. They live for about 10 to minus 10 seconds. So these pions and the muons are the first of the previously unknown new particles to be detected. And to wrap up this story of Yukawa's meson, I will tell you that the very first of these 2 common cosmic ray particles to be detected is actually the muon. So this muon used to go by the name mu meson, because when people did the experiment with with that cloud chamber picture with the positron, when they look, so I think its mass is like 106. Let me look up just to be sure. When they measure the mass of the muon, the mass was 105.7. So the mass of the muon was about 105.7 MeV over c squared. So when people first discovered the muon, they were excited. This is a new particle. We haven't seen it before. And its mass is right in the range that Yukawa predicted for this new particle, which is necessary to mediate the nuclear interaction. But that excitement was short-lived because when you look at the details of how muon behaves, it doesn't behave anything like this strong interaction force mediator should. For one, it doesn't seem to be interacting via strong force. It goes through materials more easily than electron does. In fact, the muon, as people studied it more and more, kind of behaves like an unstable, heavier version of electron. So today, we identify muon as the second lepton. So it's the mu meson, that's the old name. So people don't call that mu meson anymore because it's very confusing. Meson is a different category of particle than lepton and baryon. So we now call it simply muon, and that's the name you have seen when we do special relativity. And what this is a second lepton. And what you will begin to see is that the name lepton and baryon become misnomers pretty quickly, because some of the things that we call lepton are actually heavier than proton. But the lepton and baryon, their classification really has more to do with different types of forces interactions they participate in. So muon, the way you should think of it is it's like an electron in almost every sense, except it's heavier and it's unstable. And it's like electron in the sense there's a neutrino that's associated with muon. That's what this neutrino here is. This is not an electron neutrino, that's a muon neutrino. So it's in a dotted line because you don't really see it, but you assume their existence based on how muon goes. So it took people a little bit longer, a few more years, until they actually detected this pion, which was harder to detect because it's shorter lived. And so people had to go up higher up in the mountains to see particle tracks that they could identify as, oh, that's not muon. It doesn't look like a muon track. It's a pion track. And when you look at the mass of the pion, let me look it up to be sure again. So the mass of the pion is, so the neutral version and the charged version, they have slightly different masses. I will give you the mass for the charged pion. So mass of the charged pion, pi plus minus, they are particle, antiparticle of each other. The mass of the pion is about 139.6 MeV per c squared. So this is still in the correct range for Yukawa's Meson, and this is now confirmed as Yukawa's Meson. So the early model of nuclear interaction, the strong force, is to treat interaction between neutrons and protons. So interaction between neutrons and protons as being mediated by exchange of pions. So, I guess, exchange of pions. So if you're trying to, I guess it has to be neutral pion by exchange of pions. So if you're drawing Feynman diagram, it might look something like this. So how the nucleus is bound together, you might think of it as, well, I have a neutron coming in, I have a neutron going out, proton coming in, proton going out, and the way this interaction is mediated is by the neutral pion. Now, this is the early model. All these three particles are composite particles made up of what we now call quarks. So in the quark model, it becomes, so there's even more fundamental underlying picture, but this is a kind of starting place. And once you kind of think of it this way, you can have more fun with it. You can because there are three different types of pions, right? Or I just told you there are three different types of pions. And so when you draw the diagram this way, the only way you can draw it is with a neutral pion to conserve charge here. But that's actually not the only way you can draw it. You can actually draw it this way. You can have this neutron going to proton, and this proton going to this neutron. Then what you would say is the neutron, well, to turn into proton, you must emit pi plus. So that, and this pi plus getting, pi minus. You must emit pi minus. So that you have neutral particle coming in, positive and negative particle going out, so the charge is conserved. So this pi minus getting absorbed by this turns proton into neutron. So this is the early model of a strong interaction. And what we'll go over on Tuesday next week is the standard model as it stands today with the discretion of quark model. But I have to do a little bit of an introduction to where quark model comes from. And that takes another 3 hours. Well, not 3 hours, but including that takes another 3 hours. So let's start out with what you know, particles that you know about. So I guess I can call it known elementary particles. Well, I think to be perfectly honest, I really should put a quotation mark around elementary, because some of the particles on this list won't actually be elementary, at least the way we believe them. I can start actually categorizing them. So you know about leptons, the lightest particles, and these are actually elementary as far as we know. So we have introduced electron, muon, and we introduced why neutrino was necessary. In the beta decay, unless you had a neutrino, you couldn't conserve energy and momentum and conserve angular momentum. For all those things, neutrinos are necessary. And for the time being, I'm going to call it electron neutrino. Because we are, for my purposes, we are still in the 1930s, 1940s. People thought neutrinos were still massless. So we know these. And I guess there's one more generation, as you can see here, but we don't know anything about them yet, so we won't talk about those. And you know baryons. But let me leave a little bit of a gap between leptons and baryons because of what we talked about towards the end of last Thursday. So what particles do we know that we are calling baryons? These are some of your very familiar particles. Yeah, protons and neutrons. And those are the only two baryons that you know about. You don't know any other baryons yet. All right, and last time we introduced pions. Those fall in the category of meson because when you look at their weight, it becomes kind of in between. So you have mesons that are called pions. And I guess last time I didn't quite, well, I mentioned it, but I guess I didn't explain it, but then there's nothing to explain. There are three of these. There's a neutral pion, there's positive pion, and there's negative pion. Don't ask me why there are three. They discovered the three of them. And they're all around a similar mass. You can actually see it here. I think I can actually use this to use the particle data group website. They have an interactive tables. So this is probably what I should have done last time instead of me looking through this booklet, which you don't know what I'm looking at. So mesons, yeah. So the particles we were talking about last time, they are the lightest of the mesons. So you have the charged pions, pi plus and minus. They are antiparticles of each other. And charged pion mass is about 140 MeV. And they also discovered another particle that they ended up calling neutral pion. And you can see that its mass is very similar in the range. So that's why they called it neutral pion, because they felt, based on the similarity of the masses, that before we knew anything about this, they thought this was probably somehow related to this other pion that's the Yukawa's meson. This is the particle that mediates the strong nuclear force. Okay? So we know those particles. Oh, and I couldn't forget this important particle. We have bosons, or I guess it comes by different titles. Let me call this force bosons. So you have photon, which mediates electromagnetic interaction. And I guess this technically goes under force boson, but I'm putting it here because later we understand these to be not elementary bosons, but it's something else. And we will introduce additional force mediators that's in the standard model. So I think this is where we left off last Thursday, right? Did I forget any particles that we have mentioned so far? No? Everything good? Yes. Okay. So when you just look at this list of particles, you don't necessarily see anything missing. So like you have neutrons and protons, which are part of the atomic nucleus. You have these pions, which will explain how those neutrons. The hope is these will somehow be integral part of explaining how neutrons and protons are bound together. And you have electrons, which explain all the electromagnetic interaction. And you have neutrino, which explains all the features of the beta decay. Let's see. I guess if you're just staring at this list, you might wonder, like, what is this muon doing? Like, muon doesn't seem to be serving any function. It's just a kind of unstable version of electron, unstable, heavier version of electron. But all right, we don't know what this really is, but like what function it fulfills, but it's there. So it's in our list of things we know. And we know about photon. So this is sort of where particle physics stood in the 1940s after the discovery of pion. And this is where I say you'd be excused for thinking that this is our complete or complete-ish knowledge of the world, and all that's remaining is to fill in the gaps. You sometimes hear these quotes about like a patent office director saying everything that can be invented has been invented. That was the typical attitude around the end of the 19th century. And then maybe quantum mechanics just shook them up a little bit. But then around like the 1930s, 40s, you could be excused for falling into complacency that you've discovered everything there is to know. Chemistry is explained in periodic tables. Quantum mechanics explains chemistry. And this explains kind of, or you think it'll explain everything there is to know. And what I will show you now is how the huge paradigm shift from that view, from that somewhat arrogant viewpoint of we know everything there is to know in the world. If you talk to any proper particle physicist, what we know even better today is what we know for sure that we don't know, that our theories are deficient. That's part of the joke about your last reading question. So we know more than what we knew in the 1940s. And one of the things that we know is that our theories are missing something. So I will just kind of explain how the journey that we came to it. So I think I kind of showed you where the context where the pions and muons were discovered. They were discovered in cosmic rays, right? So I guess I'll just cosmic rays. I need a figure that has all the correct letters. This one has more of what I want. So I'll use this diagram to kind of explain what I'm talking about. Okay, so before the development of particle accelerators, cosmic rays were the main source of these exotic new particles. In fact, in this list, muon and pions, they don't naturally stick around because muon lives only for microsecond. Pions live only for 10 to the minus 8, 10 to the minus 10 seconds. So the moment you make it, it's gone. So they all have to be produced by some reaction for you to study them with. Today, we do it with the particle accelerators. But back then, before you knew about these particles, you wouldn't build the particle. Like if you didn't know they existed, you wouldn't build the particle accelerators to look for them. So back then, the source of these unstable particles was the cosmic ray, and what it's describing is, actually I don't know what it's describing. Let's just imagine there's a very high energy particle coming from the outside of the atmosphere. It's protons, helium, nuclei, and when it impacts the atmosphere, it produces a bunch of shower of secondary rays. Some of them could be alpha rays. I don't know what these represent. Some of them could be pions that we talked about. And some of these pions decay into muon. And so people were taking their detectors up to the top of the mountain and kind of looking at the tracks to try to identify, are there any new particles? You know, these are something new. Let's see if there's something that we haven't seen before. And this particle represents a particle that they had not seen before. I don't know what their early name is. Today we call it K Meson. So this is the particle that we call K Meson or kaon today. And it comes in, it comes in 4 varieties. There's the charged kaon, positive and negative. So this is showing the negative kaon. And there's 2 kinds of neutral kaon. So I'm skipping ahead a little bit because I'm telling you what people figured out after a long time. There's I guess the proper way to label them is there's a neutral kaon that's produced, and there's the antiparticle of this neutral kaon. And somehow, even though it's electrically neutral, the antiparticle is different from the particle. So this is yet another new particle that people discovered. And I guess if we are still being historically correct, the proper question to ask is, how did they know it was new? Like, what made them think that the tracks that they were seeing weren't just, another pion or another, tracks of other unstable particles, muons and pions that they have already seen before. And I guess for the quickest explanation of how they would identify it as a new different particle is to its property. So when they measure its mass, or more likely charge to mass ratio, and assuming that it has only at maximum most one charge, they can kind of infer what its mass should be. When you look at the property of the K Meson, it's heavier. So you saw that for pions, its mass is about 140 MeV per c squared. The kaon is I think, the next heavy particle. So wait, not that one. Eta is kind of, I'm just going to ignore eta. It's not very interesting. All right, those are all, okay. Those are all excited states. I'm just going to skip through them. I'm going to get to K Meson soon enough. All right, still excited state. Still excited state. Okay. Yeah, this is the problem with using the unabbreviated reference source. It's like going through a dictionary. You have to flip through a bunch of words that you don't care about to get to the key root words you want. All right, those are, once again, all excited states that I don't really care about. There's a way they organized this book, which is not how I want it organized right now for historical purposes, but we'll come back to that. Wow, I didn't know there were that many excited states. Okay, here it is. So these, we call them, so they acquired this nickname that they were the strange Mesons. So the first hint that it's a different kind of meson is its mass. It's about 500 MeV. So it's definitely heavier than pion. So that alone would have identified it as a different kind of meson. So all right, let's just keep adding to this list that we have. So on top of the pions, we know the K Meson, K positive, K minus, and then neutral K Meson, and then neutral K Meson, the antiparticle of neutral K Meson. So the very first thing that once again, is that it's heavier. The second thing that people realized was very strange, which is why it's now called, that it's where it got the name, it's strange meson, is its lifetime. It's much longer lived than the pi meson. It's kind of hard to see with the charged version, because charged version lives for 10 to minus 8 seconds, and that's sort of how long the charged pi mesons live. So, all right, that's not all that strange. But you notice that it's strange when you look at the neutral K Meson. So when you look at the neutral K Meson, once again, scrolling down, 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 down. How far do I have to go? Okay. When you look at the neutral, am I looking at both? Okay. When you look at the long-lived neutral K Meson, do they not? That's the short-lived one. Wait, where's the long-lived one? Okay. When you look at the long-lived component of neutral K Meson, which is what should have remaining after 10 to the minus 10 seconds, it lives almost as long as the charged K Meson does. And when you refer back to the pi meson, you would see that, oh, that's not the case for the pi meson at all. When you look at the pi meson, there's a definite lifetime difference. The charged one lives for 10 to minus 8 seconds, and the neutral one, it lives, wow, it's a lot shorter than I thought. I don't know why I thought it was 10 to the minus 10. 10 to the minus 17, is that right? Oh, okay, I misremembered. Anyways, but you agree it's still strange that the neutral pi meson somehow lives only for 10 to the minus 17 seconds, but the neutral K meson lives, so whichever version you look at, the short-lived version or the long-lived version, it lives at least 10 million longer. It's I read this somewhere as I was doing the particle physics thing. It's as though you came across a village of people, and people in that village were living to be, I guess, 1 billion years old, or something like that. If you saw that, then you would think, oh, somehow biology of whatever's happening in that village is different. So with the K meson, that's what particle physicists realized as they were studying the properties of this K meson, that it's so much longer lived than the other comparable mesons. So they gave it a title, Strange, and that name stuck. Through the other kind of more refined theories we'll go through, the idea of what they call, so you can kind of see it here, the idea of strangeness, which is denoted by this S parameter, that'll stick through. And this is around the time when physicists learn to become more whimsical, and so that's the strange method. So there's one more meson that I kind of skipped through the first time around, and I really need that in my list to complete what I'm going to call meson octet, and that's this eta meson. It's, I guess, a lot of property-wise, it's very similar to pi meson, neutral pi meson. It's neutral. The only difference being it's heavier for some reason. But let me keep that in the list. So you have the pi mesons, and then you have eta meson, which is heavier than pi meson, but otherwise quite similar to pi mesons. So what's starting to set this apart are the fact that they are longer lived, at least when you compare the neutral version to the neutral version. And I can actually kind of try to explain why this is longer lived. And I think I can introduce the necessary idea in the context of the pion, because this is an idea that's going to become very, I don't know, it's a common theme in particle physics. So when you look at the pion, oh wait, this was the pion. When you look at the pion, I kind of, skipped through this without bringing your attention to it. So both the charged pion and the neutral pion, they seem very similar, right? They have about the same mass, 135, 140 MeV. That seems like about the same. But for some reason, their lifetime is different by like a factor of 100. The charged pion is much more longer lived. Well, okay, not 100. I don't know why I keep thinking this lives only for 10 to minus 7. It lives for 10 to minus 17. So the charged pion lives like, I don't know, billion times longer than the uncharged version. But somehow people, so let me try to explain why that could be the case, and why that's not all that surprising. So when people discover these particles, one of the ways they kind of measure their properties, figure out what's going on with them, is by observing their decay. Because these are all unstable particles. So you look at, well, what are they turning into? You look at the charged pions, they turn into muons and neutrinos. And when they look at the neutral pion, it turns into photons. So these are the kind of decay interactions that they see. And and when you consult this chart, you see that that's the main decay mode. So pi naught, 99% of the time, it decays into 2 photons. So the common way a neutral pion would decay is into 2 photons. Good? And a common way, the most common way charged pion decays is into muon. It also can decay into electron, but only a very small fraction. So 99.99% of the time, a charged pion would decay into muon, or rather anti-muon and muon, and a muon neutrino. Right? So this kind of gives you a hint of the different kind of interactions that are involved. Because when you look at the decay of the neutral pion, then what you would see is that the decay products are photons, right? Whenever photons are involved, what kind of interaction are you looking at? Like what's the force that's involved in the decay or the reaction process? Electromagnetic? Yes? Yeah. So that's why we call photon the one of the force bosons. The mediating force mediators and the force it mediates is electromagnetic. So photons being here means you are dealing with electromagnetic phenomena. I don't see any photon here. Instead, I see a neutrino. What does that mean for what kind of interaction is involved in kind of determining the process that's happening here? What other interaction is a neutrino involved in? Sorry? Strong interaction? Do you remember any other decay process that neutrino was involved in? Someone other than Gaussian? Beta decay, right? Yeah. So you saw neutrino in the context of beta decay. And what beta decay is, the interaction that mediates beta decay, we call that weak interaction. So the presence of neutrino means there must be weak interaction involved there somehow, because it's the weak interaction that produces neutrinos. So if you have a neutrino that, in fact, neutrino is very useful for that purpose. It interacts, I guess it interacts only two ways. It can interact by weak interaction, that's where it was introduced. And we assume it interacts gravitationally. And that's it. It doesn't participate in any electromagnetic force because it's neutral. And it doesn't participate in any strong nuclear interaction as far as we know. So this being involved means there's a weak interaction involved somehow. And you can, once you kind of accept this, that somehow neutral pion decay happens by electromagnetic interaction, and charged pion decay happens by weak interaction, then you can kind of come to a piece about why this is so much longer lived compared to the decay that happens by electromagnetic interaction. Because weak interaction, as the name suggests, it's weaker. So it's like, you know, if I'm trying to move, I don't know what a good example is. If I'm trying to shake this by my hand shaking with the force of the string, then, you know, it would shake very quickly, right? What if I was trying to make it swing by just blowing on it? And I can actually kind of do it as long as I do it on resonance. But because, you know, air is much weaker, so it takes longer. And it's kind of the same principle here. Weak interaction is the weaker force, so the kind of decays that are happening through weak interaction happens more slowly. So once you accept that this is how these decays happen, then sure, they are explained. So the question is, well, why do they have to be that way? Why couldn't the decay of the charged pion happen through electromagnetic decay? So this is where this principle comes in very useful in particle physics. If, what's the adage? I think it goes, whatever is not forbidden is mandatory. It's a kind of saying in particle physics. It's really related to the context where you are looking at many, many, many interactions. Billions, trillions, numbers so large that I no longer have prefixes. In fact, the goal of building particle accelerator is to have as many collisions as possible. So because you have so many large number of interactions happening, if you have even 0.001% or if you have non-0% chance of something happening, you will see it happen. So whenever particle physicists see something not happening, like here, they never see a charged pion decaying by electromagnetic interaction. What they would say is, well, it must be forbidden somehow. Somehow, it must not be possible for this decay to happen by electromagnetic force at all. And how do you prove that something is impossible? Because it's usually pretty easy to prove that something is possible. You just do it. Then you have proven that it's possible. Somebody tells you that you can never get an A, so you study hard and you prove to them that you can, you can get an A. But like if someone actually wants to prove to you that, oh wait, this is not a good example. But if you want to prove that something is impossible, that's actually a much harder thing to prove. Because people say you can't prove a negative. Well, you can prove a negative in the scientific context. You need an entire framework of theory to show that something that doesn't happen, not only simply doesn't happen, it's also impossible for it to happen. And the framework we are going to work with is conservation laws. Because in this context, we don't really actually know a lot of physics. We don't even know a lot about weak interaction. But what we do know are conservation laws. So these are things that we believe, based on our observation, are quantities that must be conserved. So if whatever interaction or reaction requires a violation of this quantity, then this is where we can say, without having actually looked through 10 to the 20 interactions, we can say, well, the interaction you're proposing seems to violate this quantity. So we can say that's not, that cannot happen because we believe in this conservation law more than there being an exception. So we talked about this last time a little bit. So let me just recap the conservation laws that we went over. So there's a conservation of energy and momentum. And this is how the conservation law plays a role in the context of particle decay. So in fact, this can be used to prove why electron must be stable. This is an absolute statement you can kind of prove in the context of what we know. Electron is absolutely stable, and later on we'll argue that proton is absolutely stable. Is neutron absolutely stable? No, neutron decays into proton and electron. And the reason for that is neutron is slightly heavier than proton. So let me bring up a baryon table. So summary tables, baryon table. When you look at the properties of proton and neutron, so this is the proton mass. Let's remember it correctly, 938.27 MeV. When you look up neutron, it's very similar, except it's a little bit heavier. It's a 939.565 MeV. So it's heavier by a little bit, like by 1 MeV, I think. Heavier by about a little bit more than 1 MeV. So why is it impossible for proton to decay into neutron and positron? Not enough energy, right? Yeah. If it's decaying, then it's a rest frame. This rest energy is all it has. So it doesn't have enough energy to decay into neutron. But when you look at neutron has enough energy to decay into proton and electron. So this is one conservation law. And in fact, this can be used to rule out a lot of decay interactions. Question?
But a proton could decay into lighter particles.
You might think a proton might be able to decay into electron and positron. Now the thing is, we never see proton actually decaying into electron and positron, right? So so that's where we have to now start introducing the idea of additional conservation laws to explain why proton never decays into electron and positron, even though it has so many opportunities to decay into electron and positron. So, but this is a starting point, energy and momentum. This is something you're familiar with. And we also talked about conservation of angular momentum. So, and we talked about conservation of electric charge. And I've been actually using conservation of electric charge without explicitly mentioning it just now, because I was suggesting if a proton were to decay, it might decay into neutron and positron, because I'm subconsciously trying to conserve electric charge. Okay? So this is all the conservation laws that you know from physics 4a and 4b. And really, last time I just threw this additional conservation law at you. But the reason that those conservation laws are there is to exactly explain what Javier just pointed out. So, if in particle physics, anything that is not forbidden is mandatory, then you must see it happening at some point. Why is it that we never see proton decaying into electron and positron? Or, I think a muon is light enough that proton could have decayed into muon and antimuon. Or electron and antimuon. Like, why does that never happen? And this is where the idea of additional conserved quantum numbers come in. So to explain why there's such a thing as a stable baryon, people, even though we have enough energy, people came up with this idea. Baryon number is conserved. Right? And they would assign proton and neutrons with a baryon number. Let's just say, to fit with all the observations so far, say that proton and neutron each has baryon number of 1. That explains why neutron can decay into proton, because that would conserve baryon number. Then I guess here's another thing you can kind of look at. Here's one interaction that never happens. You would never have a neutron decay into proton and just the electron. Well, I guess you don't know that it never happens. Well, okay, so what we talked about in the beta decay is that, I don't know how, so I think people actually have looked for neutrino-less beta decay. So at least based on that, I can say beta decay that doesn't involve neutrino, people have looked for it, and they've never found the evidence of it. And I'm kind of swapping the chronological order a little bit, but I think I've always been kind of upfront about me not following history all that well. So in order to explain that, what you now need to introduce is the conservation of lepton number. So the reason you would introduce lepton number is to say, for example, explain why this is the only way neutron can decay. When neutron decays into proton, it must produce an electron along with a proton in order to conserve electric charge. And the reason it must produce neutrino, technically antineutrino, is in order to conserve lepton number. Because electron, it has assigning a lepton number of 1. Let the antiparticles carry the opposite of that number. Then you have lepton number 1, lepton number -1. They cancel out. So you have produced a 0 net lepton. Yeah. So this is the paradigm that we are working within. So whenever we have an interaction that we might expect to see, but somehow never happens, then we explain that by, well, the proposed interaction violates one of these conservation laws. That's why you don't see it happen. So looking back at K Meson, what you can say is, well, so with the neutral pion, you see it decaying into 2 photons, and everything there seems fine, right? No charge conservation is violated. Nothing funny happens there. Here's then what you would look for. Suppose that you had charged pion. Then could this charged pion decay in such a way that it doesn't produce a neutrino? All right, let's just make it easier for ourselves. Let's say we had negatively charged pion. What could it decay in? What are some of the possible particles it could decay into? So, I mean, obviously a muon. What other particles could it possibly decay into? Electron. Could it decay into a proton or a neutron? Why not? Sorry.
Conservation of charge.
Okay, so maybe what about positive pion? Or maybe it decays into antiproton. So, but why couldn't it decay into antiproton? Yeah, conservation of energy and momentum. So whenever you're looking at a decay, for one, you are looking for particles that are lighter than the particle you are looking for. So you're looking, all right, so it needs to decay into muon or electron. Now, it cannot decay into a single particle, then you couldn't conserve energy and momentum at the same time. It needs to decay into at least two. So then you think, oh, then I think I'm going to have it decay into this. Muon plus a photon. What's wrong with that interaction, that decay?
Lepton number?
Yeah, lepton number. So, I guess I probably should tell you this. The mesons, they have a 0 baryon number. Well, it's not a baryon, and it has a 0 lepton number. So just so as a matter of quantum numbers that people were assigning, mesons have 0 baryon number and 0 lepton number. So here you start out with a 0 lepton number. You out to end with a 0 lepton number. So you have produced a muon. All right, then I guess we need an anti-lepton to. So what about if it's a muon and a positron? Yeah, now electric charge isn't satisfied. So what it turns out to be is that once this decays into a lepton, you need an anti-lepton that's not charged. And the only anti-lepton that's not charged is neutrino. So the only way a charged pion could ever decay is by producing a neutrino, and that means it must involve a weak interaction. Okay? So this is the kind of an introduction of an idea of a new conservation law. So when people were looking at the decay of the strange mesons or the K Mesons, what they saw was this. So the charged K Meson, where's my branch? Okay, so charged K Meson could decay into, actually it decays kind of like a pion. It can decay into muon. In fact, it does that most of the time. And it can decay into electron. It does that in a very small fraction of the time. I don't know why it doesn't add up. Oh, okay, it has a hadronic mode. I guess it's heavy enough to decay into pions. But let's ignore that for now. Sorry, not heavy enough to decay into the other mesons. Yeah. And when you look at the neutral K Meson, here's what it's lacking. So before, neutral K Meson used to be able to decay into 2 photons, indicating some kind of electromagnetic interaction. Now, with the neutral K Mesons, what they see is that, let's just look at the short-lived one since that's easier. This neutral K Meson decays into 2 pions. All right, meson, so 0 baryon, 0 lepton number. Both mesons, so 0 baryon, 0 lepton number, you're fine. Energy and momentum conservation, you're fine. K is heavy enough. Angular momentum, you assume you're fine. Electric charge, neutral to neutral, that's fine. So now this is where you would begin to puzzle. Because when you look at it, so none of the existing conservation laws say that this is in any kind of a prohibited interaction. And in some sense you're right, it happens enough times. Either neutral pions or positive and negative pions, it happens often enough that you would think it's not forbidden. But what you would still need to explain is why doesn't it happen more quickly? Because people are used to saying if it's an electromagnetic interaction, this is happening over a time scale of 10 to minus 17 seconds. So if this is happening by some kind of electromagnetic interaction, why isn't it happening quickly? If it's happening by some kind of strong nuclear interaction, then it should be happening even more quickly. So the fact that this happens a billion times slower means there's something to explain. that something is causing this interaction to happen much more slowly than it would otherwise. It's possible that, I'm kind of mixing up my history about assuming you knew about weak interaction as you're looking at it. It's possible that it's involving some kind of weak interaction, even though this doesn't involve any neutrino. So what people came up with is this. They came up with the idea of approximate conservation laws. And at this point, what they introduced was the idea of conservation of strangeness. So these K Mesons are strange mesons. And going from K to pion, let's just say it gets rid of one strangeness. And getting rid of that one strangeness takes longer time, because this idea of strangeness is an approximately conserved quantity. So it's like having to take a detour. So it takes you longer. So let me just start adding to these conservation laws. So sixth one is conservation of something that they chose to call strangeness. And what I'll say is that from here on, the conserved quantity we are going to introduce, they are only going to be approximately conserved, no longer absolutely conserved. So up to this point here, they are absolutely conserved. Within the standard model of particle physics, these first 5 or 6 quantities, depending on how you count this one, they are absolutely conserved. There's never any exception to those. If you ever find an exception, you win Nobel Prize. But starting from here, they are approximately conserved, as in certain kinds of interactions will violate it, no longer conserved under certain kinds of interactions, weak interaction, but the other interactions will conserve this. Electromagnetic and strong nuclear interaction conserves the strangeness. What we are going to talk about now, it goes by the playful name Eightfold Path or Eightfold Way. I want to say Eightfold Path. It's the physicists who came up with this way of organizing newly discovered particles was his name is Gell-Mann, he's not Asian, but he was very into Eastern mysticism. I think this is taken from some Buddhist things. So this is how he started by organizing these mesons. So you have these 8 particles, and they can arrange into a hexagonal shape of a sort. So let me, I have a reference to check if I do this wrong, so we'll check it after I'm done. So the way he organized is this. I think he put the pions along a horizontal. So pi neutral, I want to say it's pi minus here and pi plus here. And at the same center, he would also have the eta meson, because he's looking at these two as similar versions of each other. Eta is the heavier version of neutral pi meson. And he arranged these K mesons kind of around it. So this is where I have to be careful. I think. I want to put the charged K minus here. Then you do have one of the neutral K mesons here. And you would have the positively charged K meson here, and the antiparticle version of the neutral K meson there. And there's actually some scheme to this. I don't want to the baryon one is one that's more intuitively easy to understand. But let me just point out some of the scheme that's developing from this particular arrangement. You can see that these are arranged along a pattern of having the same charge. These diagonal lines, you would say charge of -1, charge of 0, charge of +1. And you can assign, I guess, just one more line by strangeness. So I think I was just looking it up in the table. I think to be correct, the strangeness you would assign is these particles here have strangeness of 1. These have strangeness of 0. These are the unstrange particles. And this one at the top would have the opposite strangeness of -1. I think that's right. But let me just double check. Yeah, I think that's right. So this is one pattern that you have. Before we go on further, let's just double check one of the references I have to make sure I didn't misremember some things. I mean, the overall pattern, I'm sure I got it right. It's a question of did I flip some corners around? So let's see. I have a diagram here somewhere. So I just, the way it's plotted there, these two are flipped around, but otherwise I didn't mess up anything else, right? And I guess if this is flipped around, then this is kind of the line of constant charges the same. But this is really what I'm looking at. So I forgot to label one of the antiparticles. So I need to have given the antiparticle distinction here. So this is the first neutral K Meson, which is associated with the strangeness of 1. And there's apparently a second neutral K Meson that's not associated with the strangeness of 1. And this would be discovered through observing various interactions. They would look at like this particle, by everything else, it should be neutral K Meson, but it doesn't decay like this one does. It decays in a way that, it decays in a different way that involves a strangeness changing differently. So this says strangeness of -1. Good? So this is a bit, I guess, not as well motivated. I started out with this because we've been talking about Meson. But the easier thing to, by the way, this is what's called Meson octet. But what's easier to motivate without knowing a lot of particle physics is actually a pattern of the baryons. So far you guys have learned about 2 baryons, right? We are going to talk about 6 more of these. So these are actually very particular type of baryon. So these are the baryons with spin 1/2. With the baryons, as in particles in the range of the mass of the neutrons and protons and higher, you can actually have spin 3/2 baryon. So within the limit of spin 1/2, we are going to have 6 more baryons. And particle physicists have discovered 9 more spin 3/2 baryons, spin 3/2 baryons. So let me just write it down here. Spin 3/2 baryons, 9 discovered. So this is what we call particle zoo. So we start out with trying to describe elementary subatomic particles, and these start to multiply like elements. So indicating there might be some kind of underlying structure, that these baryons and mesons that we are looking at, maybe they are not elementary. Maybe they are made up of something more. And it's that underlying structure that they were trying to figure out. And Gelman's, let me write down the name somewhere. I don't know how to pronounce his name. I'm sure he pronounced it some way. I want to say Gelman, but I'm not sure if that's right. So Gell-Mann's model is what stood the test of time. And so there's an actually underlying structure here. That's why it's arranged this way. And with the baryons, with the spin, both the spin 1/2 and spin 3/2 baryons, you can kind of arrange them more easily. So let me actually tell you the particles that were discovered. And this is where I stop actually having the things memorized. So what I'm going to do is I'm just going to go to the beginning of this note, where I list all the particles, well, not all, many of the particles that have been discovered. So, yeah, all right. So you recognize some of these particles, right? You recognize the proton, neutron. You recognize the pions and the K Meson and the eta that I just mentioned without introducing it. So those are good. And these are the 6 additional baryons that exist, that people have found in looking at cosmic ray interactions. And the main way they would categorize it is by kind of looking at their decay products. By looking at their decay products, they can assign charges, like it has charge 0. If you infer somehow that it decays into 2 photons or something like that, or 2 neutral pions. And they also these get assigned some kind of strangeness. But when you look at baryons, you can actually start to see a pattern that's just built in there without you having to struggle through it. Look at how wrong color. Look at how proton and neutron are similar in mass. Do you see any other particles that are similar in the way neutron and proton are? Right? Lambda, or what got named as lambda, and then the 3 sigma baryons, they all have the same or similar mass. And the Xi, this is the capital Xi, C. This is a capital Xi, neutral Xi and the negatively charged Xi. And for some reason, they've never found a positively charged Xi. So, but these masses, like with the atomic weights, become a hint for maybe there's something periodic here. Maybe there's some pattern here that you can associate with the energies of these particles. So let's just kind of arrange them. I guess so I'm going to call this baryon, well, people call this baryon octet. It's not my name. And kind of the natural way to do it is, let's go from light to heavy. And so you could have put, I don't know how it goes. I think I want to be at the most negative charge on the leftmost and the most positive charge on the rightmost. So let's go then neutron and proton. All right, then I do my next row. Most negative particle is sigma. So minus sigma. I have neutral sigma, and I have positive sigma. And since I have two particles that are definitely different, they have slightly different mass, but same charge. So I'll just put lambda in the same kind of box as where I'm putting neutral sigma. And here the most negative is actually negative. So let's put C minus here and C plus C neutral here. Okay. So these are organized by weight. And if a lot of this isn't making sense in the sense that you don't know why they were doing it, that's perfectly fine. I teach this version only because that's what stood the test of time. I'm sure theorists of the time tried many other crazy shapes that just didn't work out, or tried many other crazy ideas that we don't talk about them anymore because they turned out to be wrong. So this is just what turned out to be right. And once you kind of arrange them this way, then you begin to see some pattern that you can notice again. There's a pattern of charge, which is kind of built into how I built them. This is the line for negative charge, neutral charge, and positive charge. All right. And so these baryons can be assigned strangeness. And it turns out after they were done assigning strangeness, this is what they found by, so you assign strangeness by looking at decays. Any kind of quick decay, you can assume that this kind of decay conserved the strangeness. So for example, the sigma baryons, like sigma minus, I think it's heavy enough to decay into K Meson. So they probably saw decay of this into K Meson. Let's just double check to be sure. PDG. How to call these things? Okay, sigma baryons. So let's just say sigma minus, what it decays into. It decays into, so mean life, it's not very long-lived. Well, 10 to minus 10 is actually pretty long. Anyways, let's see what it decays into. Magnetic moment, decay modes, okay. Oh, wait. It all decays into lambda pi minus. Okay, so this is how you would argue. So I guess it's not actually heavy enough to decay into K Meson. But so it's not heavy enough to decay into K Meson and another baryon. So it does decay into pi Meson, but as I was commenting on as we were scrolling through, its lifetime is pretty long, 10 to minus 10 seconds. So you assume that decay must have required change of a strangeness. So with that, you can infer that, then I guess let's say this has strangeness of 1. This has strangeness of 0. And when you look at sigma, I don't think sigma is still heavy enough to decay into K Meson. So not sigma, Xi. I can't really say the words right. Let's look at Xi baryon and see how long it lives. Maybe it's longer lived than sigma even. No, I haven't looked. I probably should have looked. So you can see that they assigned, sorry, I messed up. Strangeness of -1. They assigned the strangeness of -2. And that's probably based on something like lifetime. Let me first look at the decay modes so that I have a better idea of what it's decaying into before I start talking. Okay, so it decays mostly into lambda, which from their study earlier has a strangeness of -1. So if this also has a strangeness of -1, then it should decay reasonably quickly because you're not trying to violate strangeness conservation. But when you look at the actual lifetime, mean life here, it still has lifetime of about 10 to minus 10 seconds. So it probably also involves violation of strangeness. So this now has an additional strangeness of -2. So this organization is a little bit more, I guess, easy to motivate because these rules come from the masses, and looking at the strangeness to assign comes from looking at the lifetime of these heavier baryons. Yeah? So, okay, maybe at this point you are beginning to see that there's a pattern there, but I don't know if you guys ever listen to, does anyone here have heard anything about time cube? Maybe you guys are too young to have heard about time cube. It's one of those internet crank theories. There's a guy who used to run a time cube website. He said time is cubic. So when you see crazy theories, one of the things is this. You can almost explain anything. Like given some set of facts to kind of come up with some idea to just explain all the known set of facts. It's not all that hard. Anybody can do it. In fact, that's what we think early mythology was. People look at thunderstorm, thunder striking someone, and it's easy to think, oh, one of the gods is angry at the tree. And that's, at least that's how we think of what the ancient thinking was. And even today, that kind of instinct hasn't changed. So if all this is what it is, you have all these newly discovered baryons and mesons, and you're just fitting them to a pattern that looks pretty, then that's not very valuable. Like, what can you do with it? The reason anybody know how to pronounce this name? No. I'm just going to say Gell-Mann. The reason Gell-Mann's theory stuck is because of really a striking prediction he made. So as I was alluding to earlier, there were just so many particles discovered that scientists were getting frustrated with all these new particles and no coherent theory to explain them. And Gell-Mann's theory was one that actually predicted existence of a particle, a new particle, down to the correct mass and how to produce them. And that comes with the next set of baryons. So I said with the baryons, there are actually spin 3/2 baryons. And I think I have a table of them somewhere here. Let me scroll to the table. Okay, got it. Yeah, because I need 9 of them. And Gell-Mann is the one that Gell-Mann predicted the 10th one. So hopefully, unless I messed up, I should have listed the 9 of them here, because those are the ones that were first found. So delta baryons, all spin 3/2, and apparently there's one with a charge of +2, but no charge of -2. So delta baryons, and there's the sigma baryons that are somehow different from the previous sigma baryons because they're heavier. And there's Z baryons again, but somehow different from these because they are also heavier. And there's, did I mess up? Yeah, okay. I don't know why I listed this one. So omega baryon. Yeah, so this omega baryon is, I don't know if I want to cross it out. This omega baryon is the one that was not yet discovered. So people had known all these 9 baryons, and Gell-Mann's theory predicted this omega minus. And he predicted what they would look for, interaction that would produce the omega baryon. So you can kind of arrange these baryons a similar way as how we arranged this. So let me just do that. We're just going to arrange it by mass. That's how things seems to have worked so far. So let's do that again. So this pattern is going to look a little bit different because the lowest mass, instead of having only 2, apparently I have 4 of them, the delta baryons. So, so you have delta minus, delta 0, delta plus, and delta double plus. You have, and on the next row, this is the next set of particles that are now slightly heavier. You have sigma minus, sigma 0, sigma plus. There's technically an asterisk there to indicate it's different from this, but I'm going to skip it in the interest of time. And there's the Z baryon, 2 of them, C minus, C plus, not plus, 0. Now, something is different about this shape compared to this shape. Like the hexagonal shape, it's complete on its own. Like when you look at it, you don't think something is missing. Like it's complete. I don't have to do anything with it. As you look at this trapezoid, do you feel like something is missing here? What's missing? The tip is missing, right? Like you feel like it should be triangle instead of trapezoid. I mean, at least that's the inspiration. And so this is the particle that Gell-Mann predicted, that there should be omega minus. That there's an additional particle that fits the pattern of these spin 3/2 particles. And once you have it all laid out, then you can kind of do the same thing we were doing before. So there's a kind of charges, pattern of charges that follow, right? Q equals 2 here, all the way down to Q equals -1. That's why it's omega minus. And the strangeness, it ought to have this pattern of strangeness, -1, -2. I guess that's what you knew about this omega particle. It has strangeness of -3. That's probably why it's rarer. If a strangeness violating interactions happen slowly, then like to get from strange of -1 to here in one step will probably be impossible. You need to start out with something that has strangeness of -2, or you need to produce. So it has strangeness of -3. It's more strangeness than other particles that we know so far. And and this is how Gelman predicted the mass of the omega particle. He kind of stares at this masses for a while. Okay, 1232. Next step, 1385. So the difference is 153, right? Add 153 to this, you get. So if you added 153, you would have gotten 1538. Hey, that's pretty close to this. It's only off by 5. So let's just add another 150 to this. Then you would predict the mass of around 1683 or so MeV. And I don't know if you can see it beneath me trying to erase it. When they actually detected a particle, it had a mass of 1672. So within 15 MeV, he was able to predict what the mass of this last previously undiscovered particle would be.